Welcome. The purpose of this brief video is to introduce the conventional empirical rule. This rule is often called the 68-95-99.7 rule, which, if you'll forgive me, is probably one of the stupidest names I've ever heard for a mathematical or statistical rule. And sometimes it's actually referred to as the 68-95-99 rule, which is actually even a bit more deceptive and a bit more inappropriate. It turns out I dislike this rule as much as I dislike the name. But I'm going to cover it briefly because you may encounter it in other courses, and even though I'm going to present a more refined version of this, it's still good to be aware that this rule is actually out there. Now, the first thing to note is this rule only works for normal distributions. This is what we refer to as a rule of thumb, or a heuristic, or an approximation. How does the rule work? Well, approximately 68% of the data lies within one standard deviation of the mean if the data is nearly normally distributed. Within is interpreted mathematically using the plus-minus symbol. Mu plus minus the standard deviation is how this is often written. And the idea is this means that you both add one standard deviation to the mean and you subtract one standard deviation from the mean. And if you take this interval of one standard deviation below and one standard deviation above, you should capture about 68% of the data within that interval. Continuing, if you look at two standard deviations above and below the mean, within that interval you should capture 95% of the data. And as the name suggests, if you go 3 whole standard deviations above and 3 whole standard deviations below the mean for a normally distributed data set, you should capture about 99.7% of the data. Again, 1 standard deviation above and below captures 68%, 2 standard deviations above and below captures 95%, 3 standard deviations above and below captures 99.7%. Well, let's look at this in action briefly to get a better sense of what's actually happening here. So here's a data set that is perfectly normally distributed. It has a mean of 50 and a standard deviation of 15. On the left, we see a frequency distribution table in increments of 5, which we'll later note is 1/3 of the standard deviation. So our class width is 1/3 of the standard deviation. Or said another way, 3 whole classes is the length of 1 standard deviation. Now, if we look at the center, the average, the mean of this data set, 50, and we go 1 standard deviation below would take us down to 35, 1 standard deviation above would take us up to 65. If we ask what proportion of the data is in the interval from 35 to 65, we see that there are 1,366 values out of the total 2,000 values represented in this data set. This turns out to be 68.3%. Now, the rule predicted that there should be about 68%, and as the rule goes, 68.3% is relatively close to 68%. Continuing this once more, we see that for 2 standard deviations above and below the mean, 2 standard deviations would be 30 units, 30 above 50 and 30 below 50 gives us the interval from 20 to 80. Looking in the table from 20 to 80, we see that there are 1,910 values. Dividing this by 2,000, the total sample size gives us the proportion 95.5%. Once again, we notice, as the rule predicted, it is close to 95%. If we continued this for 3 standard deviations, we would get 99.8%, which again is very close to 99.7%. Now, this shows the conventional empirical rule. Okay? If we move 1, 2, or 3 standard deviations above or below the mean, we capture a given percentage. The numbers 1, 2, and 3 make perfectly clear sense. However, the percentage choices that were given, 68, 95, and 99.7, in truth, the only real value of practical use there would be 95%. So let me give you a little bit of why I think this rule actually sucks as rules go. Okay? A rule of thumb is by definition a rule to obtain an approximation. And if you're going to use approximations, they need to be reasonable, workable numbers, practical numbers. Okay? So let's look at the numbers in this rule. 68, 95, 99.7. Who would say something is approximately 68%? I think most people would far more likely to use a rounder number for the approximation, for example, 70%. addition to the far more extreme, when, if ever in your life, did you ever say to yourself, hey, what is 99.7% of this thing that I'm interested in talking about here? Simply put, as a percentage goes, 99.7% has no practical or pragmatic purpose. Simply put, this is a crappy rule. Alternatively, the count by thirds empirical rule is far more pragmatic for the people who might wish to use an approximation that this rule provides. The advantage to this old, traditional, crappy rule is that we are counting by whole standard deviations, 1, 2, and 3. But the problem is that the resulting percentages, rounded or not, are really not that useful. We essentially sacrifice usability just to count by whole numbers. So let's look at an alternative empirical rule, a rule that uses less nice counting numbers, if you will, but substantially more useful percentages. And for what it is worth, the degree by which the old percentages are not useful is in no way comparable to the degree of less niceness of the proposed counting numbers suggested by the rule I'm about to propose next, the count by thirds empirical rule. And I will continue more on this in the next video.